So so I'm from Grenoble. I came in my car this morning, and well, the objective of my talk today will be to reconciliate the wave aspect of light with the particle aspect of light, with the two new modern instrument technologies, and to illustrate and to let you understand physical principle behind those new modalities and how they are useful for the diagnosis of pathologies. And well, beyond these new concepts, how can we improve once again by combining these two aspects of light, the future of X-ray imaging technology. So just a recap as an introduction, medical imaging has been invented with X-ray, with this image of the woman of Röntgen in 1895, and that's why he got the first Nobel Prize in physics. And in 1971, the invention of this scan by Armstrong and Tomac, that's had the Nobel Prizes once again. And since then, well, X-ray imaging has been the same, has been using the same principle. And now we are fixing major evolution of X-ray imaging, which are the color scan, and the wave aspect of, the use of the wave aspect of light for getting this what we call phase contrast imaging. That will be the next major evolution of X-ray imaging. But first of all, I need to introduce you the principle of what the synchrotron is, because all those technologies are coming from the synchrotron. And here, close to here, whenever we have the chance to have this very large structure, as you can see here. You see about here. The dimension of its gigantic. It's 800. The inner part of the circle is 830 meters, so it's a gigantic structure. And the more interesting the bar. Gigantic, and it offers very nice properties that we're going to exploit. The first one is the eye flaps. So we are 10 to 6, 10 to 7 times brighter than the space source in the hospital. And what we have also is what we call a parallel distribution, so special coordinates, but that light is produced. Light is produced somewhere here in 60 different lights, and we are 150. So the spot is 60 micron, and we are 100 meters from that. So we can consider that as a point source, like we can consider that the sun, as big as it is very far, but all the rays are coming parallel to the and we can assume the same principle. So that's it. That's the synchrotron is a laser for X-ray. It produces X-ray as laser in terms of concentration of light, in terms of spatial brilliance. And the way it works is this one. So, before the video, the way it works is that we extract electrons. So we extract some electrons from a metal wire, for instance, here from the center, accelerate it to the energy of, in the order of mega electron volts, which is the energy of, for instance, your therapy. And then it enters, so it's not very visible here. It enters a circular structure that we call the booster. Surprised that the keyboard doesn't work at all. It enters this, you can see here a circular structure. It reaches the energy speed of 6 giga electron volts. So 99% of the light speed, okay, or mass for an electron, mass. Okay. And then it enters what we call the storage ring. And in the storage ring, we have beam lines. And here at the at the SRF, at the European synchrotron, we have 42 beam lines, so 42 different microstops that uses this light. And the way it works is this one. So the electrons are traveling at the speed of light, and then they enter into a high magnetic field, which is about Tesla, so the same as an MRI. And due to the fact that they are losing some energy, they are creating this lose of energy creates the lights. Okay. But the way we do synchrotron imaging is more or less the same as we do normal X-ray imaging, except the fact that so we have the light that is produced in this what we call wiggler, high magnetic. And this creates the light that we get because of the flux from the light. And then we put the sample, and then we have the detector. So, contrary to normal CT scan, where you rotate around, here we rotate the sample. But otherwise, this is the same principle as X-ray imaging. You have an X-ray source, and you look at the light that has crossed this sample. And for instance, here you have an image of rats at 21 micron, a living rat at 21 micron, where you see the bones, structure of the bones, you see also the soft tissue and all that. So, the first exploitation of the usage of synchrotron was to create what is called the spectral X-ray imaging, and that has been translated to the clinics in New York, and we're going to see how it works. So first of all, I wanted to thank you. So here it was just the result project. The idea just was to get for different application, for stroke and for osteoarthritis, some regenerative therapy, and we want to follow. And to study that, what we had was cells, cells that were and to enter a better graft, we had this iodine to label it. And we're going to see how this enables us to have an image of cells, the iodine, and the soft tissue. But here is an image that we can have in a monochromator, and here is a typical image that we have, and we see this here, both, and the structure inside the brain, you don't know what it is. Okay? With a conventional X-ray CT helps people distinguish between gold or is it own macro-classification, for instance, or if we are in election, the things on Donald Trump, but we will see how it works. So what we are aiming at here is what we call the K-edge imaging, which is another Nobel Prize by which from Einstein. Einstein got this Nobel Prize with explanation of this phenomenon function. And what we see here is for the energy that we are using, generally wavelength that we are using in X-ray radio, X-ray imaging. What we see is these possibilities. From these possibilities, we are through spectrum. And those responsibilities are actually linked to. So here is the what we call the K edge is the energy of the atom of the K layer of the electron. You have also that's for L. This moves that's lower end. And what we're gonna use here is this continuity. So, but first of all, the physical principle of it is this one. So let's imagine that you have different case. In one case, the incidence into important energy is below that edge of the atom. And in the second case, you have an incidence into important that has an energy which is higher for the K. The first case, and most of them, it's that you do not have an interaction with the X-ray and the photon, and this can happen. The second structure is the same. The second direction that might alter at this energy is what we call the Rayleigh scattering. The Rayleigh scattering is an interaction between photon and electron that has the same, and the incidence photon has here the same energy. Then we have what we call the Compton scattering. That's general. Try to avoid that. And here, the only difference with the Rayleigh scattering is the fact that here you have an interaction directly with the electron that has been ejected, for instance, and you have an energy that is from it. But what can happen in the last case is the photoelectric effect. So what we call the absorption of X-ray is this one. So if you have an energy that is smaller than the energy of the atom, you have really a good chance to interact with a electron. While if you have this big electron, eject the electron, and for electronic stability, you have another electron that is going to the other layer, inner layer, and then observe this at this specific energy. You have maximum chance of getting this at the exact energy of the wave. So the idea, thanks to synchrotron, can have flux that is gigantic. What we do is that we obtain an image. We can monochromatize the image, saying that we have only one wavelength. Okay? And because we have one wavelength, we can do an image above this gauge and below this gauge. What we observe here is very small aggregation for other elements. This is water. And thanks to this, you can have an image of the iodine. And you have real image, just the iodine, and you can be quantitative in the concentration. Know exactly how much, how many concentration, what is the concentration. And you can do such a thing also above and below the gauge of. So, in terms of equation, it's this stuff. So, have this. So, Actually, it's mu is the what we call the absorption coefficient is the this attenuation which is expressed in general in centimeter by line. And what you are sensitive to is this difference is of the thing. And then what we do is a simple linear system. And in each voxel, we assume that you have a fraction of, for instance, iodine, gold, wire. And what you do is that for one energy expressed each the attenuation, let's say, the attenuation that you measure by the linear by a fraction of those times. And then you solve this linear equation and you get this kind of equation, which is simple to solve. Then we have the concentration of iodine here in each voxel, differentiate between iodine. So in another image, which is more here, you have a conventional view. You cannot distinguish between the concentration. You see some brighter than the other. But thanks to this decomposition, it's clear that we tried to have this concentration of iodine with the and letter A. So here, just to show that it's feasible to have the same notion and stay and being able to know what is the concentration of this element. And in our case, what was invested was concentration of cells that we had. And this compared to just validate the measurements, these are the gold measured by and this is the gold measured by mass spectrometry, meaning that we are completely linear. We are overestimating here iodine and concentration plus gold, but we are very good. And then comes this fantastic tool that we have, that you guys have in Lyon, which is spectral analysis available as a type, which has more or less the same principle, but because the flux is smaller, but they have spectral, but they introduce this X-ray source, normal X-ray conventional source, and as what we call the spectral detector. So a detector that is able to compose different wavelengths, different sub-energy. Okay. So we are able to do the same principle of the edge, but with let's say a source and larger bits that we can get. But next to that, we are able to have this decomposition instance. So it's probably not the same price, but have this normal conventional image that you can have this decomposition. And once again, here you have linearity to the concentration that is measured by IC and gold measured by the clinical units. And so thanks to that, you have, for instance, gold, and you can estimate in your animal with a device that does not cost $2 billion, but only some million, can estimate the concentration of compressed agent that you have. here, on the cells. So in the breakthrough projects, especially in the Clément PhD, what we done is the comparison between what we can get from the supercon and the it was an INM project that will end in 2 months from now, and that gathered that from and lots from another and another. What we measured is this comparison. So what is interesting is that you have a perfect linearity between the goal measured by spectral CT and the one measured by the synchrotron. And in the phantom, you seem to have also a linearity. But here are the images in vivo. So here the protocol was, we were able to image in vivo at the synchrotron, and 2 days after or 2 days before, we obtain also the image of the CT. And what we can get here, what is interesting, is that the clinical drugs for gold is as precise as the synchrotron. Have the same spectral resolution, the observation it gets a fast control that you have is the same. While for the iodine, it's a bit trickier, and you miss some of the structure because the spectral CT was not sensitive enough. But we can do such a thing also. So just to show some nice condition, with the mice articulation here is the same to have this cells and this iodine gel just how it treats the arthritis. And so the first patient was imaged in 2019 in Lyon at the CERNET. It's really a first human and first in the world imaging of this technology. And since then, they have shown that it's really interesting for either the patient's imaging, but also for practical imaging. And they want to that's for instance, they have published some interesting features about the cartilage, which is really the next to see conventional CT. And interesting stuff about nerve that have been compressed. And what you can get here is almost synchrotron image, in the sense that you can have virtual one here this unique and really interestingly, you see a really good of the trabeculus of the finger. Something here what they do in this field as well. But you see some defects in conventional CT image. So to put that in a nutshell, thanks to this technology here, that is available in Lyon, you can image better at a lower radiation dose, and you have very nice image, and you can even here distinguish what's challenging on why you have this lower radiation dose. So that was just to introduce you. Next, the actual future or X-ray imaging that happens now at campus. But I've been essentially I'm here essentially to present what is X-ray imaging. So is that's use the aspect of waves, wave aspect of light, which is the next, let's say, X-ray revolution, and we are already facing it because we have some results on clinical trials. So first of all, because we are not necessarily very familiar with these sets, at least that was not during my studies. So I wanted to show you some videos from a guy named BRUN that is that puts to data, which is mathematician, that is who is producing some videos on YouTube that are really, really interesting. So explains what's and what I'm going to use afterwards. So this video is 8 minutes.
Of why passing through a medium would change the speed of a light wave at all. And for this, I want you to think of your material, like glass, as being broken up into a bunch of distinct layers, all perpendicular to the direction that light is traveling. And we'll start by focusing our attention on the effect of just one material, like glass, of why passing through a medium would change the speed of a light wave at all. And for this, I want you to think of your material, like glass, as being broken up into a bunch of distinct layers, all perpendicular to the direction the light is traveling. And we'll start by focusing our attention on the effect of just one of those layers on the light wave. The true effect would be minuscule, but if you'll let me exaggerate it for a moment, what it does is kick back the phase of the wave. And maybe it's worth a brief aside to make sure we're all on the same page when it comes to wave terminology. If you go and graph the function sine of x, when you put some term in front of it, affecting how high that wave oscillates up and down, that's what we call the amplitude. When you put a term in front of x, this will affect how rapidly it oscillates. If this is meant to describe a wave over time, that term would be called the angular frequency. Whereas if it's meant to describe a wave over space, that constant would be called the wave number. Then if you were to add some other constant inside that sine function, and notice how as you change what that constant is, it sort of slides the wave left and right, that term describes the phase of the wave. So when I say that our light wave hitting a layer of glass causes its phase to get kicked back, I mean if you take whatever function describes it before it hits the glass, then the function describing it after that looks almost the same, just with a little extra something added to the input of that sine function. Like I said, in reality that'll be a very small number, something proportional to the infinitesimal thickness of that layer, but I'll keep drawing it as something exaggerated and keep track of the value of that phase kick over here on the left. Let's say you go and add a bunch of other layers of the glass, each one also applying their own kickback to the phase of the wave. The question for you is, what does that new wave look like? If the value of that phase kick applied by each layer is something really close to zero, then the wave is hardly affected at all. But the larger that phase kick, the more the wave kind of gets squished together among all those layers. Admittedly, right here it looks all kaleidoscopic and weird, but that's really just because I have a discrete set of layers, each applying an unrealistically large kick. Notice what happens if I smooth it out by doubling the density of layers, but having each one only apply half the phase kick. And then I do that again, I double the density of the layers, but have each one only apply half the phase kick. As I continue this over and over, approaching a situation where you have a continuum of glass, each layer applying just a tiny infinitesimal phase kick, what you end up with is identical to, indistinguishable from, a wave that's simply traveling slower, oscillating up and down with the same frequency, but with a wavelength that's been kind of scrunched up. This right here is the first key idea with the index of refraction. Instead of asking, why does light slow down in glass? What we really need to ask is, why does its interaction with a single layer of that glass cause a kickback to the phase of the wave? And then when we want to get quantitative and understand exactly how much the light slows down, which is critical for understanding why it depends on color, instead the real question is, how strong is that phase kick? From here, it's helpful to turn back to the fundamentals of what light even is. This is something we talked a lot about in the last video, but a little review never hurts, so let me go over the essentials. As many of you know, light is a wave in the electromagnetic field, but here we'll just be drawing the electric field. The electric field associates each point in 3D space with a little three-dimensional vector telling you what force would be applied to a hypothetical unit charge sitting at that point in space. The key thing going on with light is that if you have a charged particle and something causes it to wiggle up and down, that results in these propagating ripples in the electric field away from the charge. And that propagation is traveling at the speed c, the speed of light. Whenever those ripples happen to reach another charged particle, they cause it to wiggle up and down, albeit a little more weakly than the initial wiggle, and that in turn causes its own propagations. The way we described this in the last video was that if at some point in time a charge is accelerating, then after a little delay, which depends on this speed c, the existence of that acceleration induces a force on another charge. We went over the specific force law describing this. It's something that can be derived downstream of Maxwell's equations. But for our purposes here, the main thing to tuck away in your mind is that the amount of time it takes that initial acceleration to cause any kind of influence elsewhere travels at exactly the speed c. And really, you should think of c not so much as the speed of light per se, but as the speed of causality. It determines how fast any kind of influence travels. It's just that one of multiple consequences of that is that it's the speed of light. In particular, when you get a charge oscillating up and down in a nice clean sinusoidal motion, you can think of these rippling effects in the electric field as describing the force that would be applied to another charge sitting there as a result of that past acceleration. I will freely admit that I had a bit too much fun in that video just simulating how the electric field responds to accelerating charges, that I'm kind of doing the same thing here. But there are two important facts for our pursuit of the index of refraction. The first is that when you have multiple different charges oscillating up and down, the net effect on the electric field is just the sum of what it would be for each individual charge, which is kind of what you would expect. And then the way that it shakes out is that if you have a row of charges oscillating in sync with each other, or for our purposes today, a plane of charges, all wiggling up and down in sync within that plane, then the effects of each individual charge tend to cancel each other out in most directions, except perpendicular to that plane, they actually constructively interfere. This is how you can get a concentrated beam of light. That's the important thing. If you have a layer of charges wiggling up and down in sync with each other, then even far away from that layer, it produces this nice sinusoidal wave in the electric field that we're so fond of drawing to represent light. When I draw a light wave like this, it's really only depicting the electric field on a single one-dimensional line. A more full picture of light in 3 dimensions would look something more like this. That tends to be a little bit busier, so usually we just draw the sine wave. So, thinking back to the question of why interactions with a layer of material would cause a kickback to the phase of the wave, let's start thinking it through. When a light beam enters a material, like glass, then it causes all of the charges inside that material, electrons or maybe the occasional ion, to wiggle up and down in response to that light wave. You might think that adding together all the propagations from all those charges is a complete nightmare, but we can think about it one layer at a time. As the light wave causes this layer to wiggle up and down, that wiggling produces its own second-order light wave at the same frequency. And it propagates in both directions perpendicular to that layer. The overall electric field, then, looks like the initial incoming light wave added together with the second-order wave. By far the most distracting part of what's going on here is everything on the left, and this actually corresponds to the light being reflected back. And from experience, you all know that when you look at water or you look at glass, light not only goes through it, but some of it gets reflected back. And we could have a whole interesting discussion on quantifying exactly how much, but in the spirit of staying focused, we will completely ignore that for today and only focus on what's happening to the right of that layer. You can probably predict what I'm going to say. It turns out that when you add that second-order oscillation, the overall effect is almost identical to the incoming light, but just shifted back in phase by a little bit. And then because many successive shifts to the phase like this are the same thing as light slowing down, this will ultimately explain the index of refraction. Of why passing of Which is why exactly light slowing down would imply that it bends as it enters a medium. There's a common analogy, which is to think of something like a car or a tank, where it turns a little bit while one side of it slows down before the other. And although it's a very visceral and memorable analogy, it's not like light has wheels, and it also tells you nothing about how to be more quantitative and derive the formula describing exactly how much light bends. Here's a better way to think about it. If you have some light wave shining into a material like glass, if it slows down, notice how that means that it gets kind of scrunched up. If its wavelength in a vacuum was some number lambda, then the wavelength inside this material, where it's gotten slowed down, is something smaller than that. Here I am drawing the wave only on a one-dimensional line, but we need to understand it in at least 2 dimensions, where every point on this plane, for example, is associated with a little vector in the electric field oscillating up and down. This particular animation is a little bit messy and hard to follow, so it might be clearer if instead we simply color every point of the plane such that those points are white near the crests of the wave and then black away from the crests. You can still clearly see the wavelength as the distance between these crests. It's exactly what we were looking at before, just drawn in a different way, and in particular notice how they're scrunched up inside the glass. If that glass were positioned at an angle, think about what happens to each one of those wave crests. As it hits the glass, the lower parts slow down before the top parts, causing it to get sort of smeared out. It reminds me a little of the rolling shutter effect. And overall, the wave crest ends up at a different angle. When you take into account the fact that for a beam of light, the beam is always perpendicular to those wave crests, this means your light has to turn. And moreover, you can calculate exactly how much it needs to turn. Think about all those waves in the vacuum, with some kind of wavelength lambda 1 sitting between them, and focus on all the points where those crests intersect with the boundary between the vacuum and the glass. But then consider those wave crests inside the glass. If it was the case that no bending happened, then because the wavelength is smaller in there, when you look at all those intersection points, they would have to be closer together. But of course, that can't happen whether you're looking at it from one side or looking at it from the other. Those intersection points are all the same. So the only way this can work is if those wave crests inside the glass were oriented at a different angle. And you might mentally imagine turning them with a little knob to find the sweet spot angle where all those intersection points line up. And for those of you into exercises, you could take a moment to try to write down the specific equation telling you how to relate the wavelengths inside and outside the glass with the angles between those wave crests and the boundary itself. If you do this, what you write down is effectively the same thing as Snell's law. You just have a tiny bit of added work to relate the relevant angles here, and then to note how the speed and the wavelength all depend on each other. Which is why exactly the most intriguing question of them all, which is how the index of refraction can be lower than 1. Faster than the speed of light. So this really, what that seems to imply can be lower than 1, since what that seems to imply is that the speed of light through a medium would be faster than the speed of light. So this really does happen, and it's not as wild as you might think. If you think back to how everything in our discussion arose from how a layer of material can kick back the phase of a wave, there is no reason that the layer of the material can't also kick forward the phase of that wave. And when you have many successive layers all kicking forward the phase like this, it gives the illusion of a wave that's traveling faster than the speed of light, in the sense that those crests genuinely are moving faster than c. In fact, when you unpack the math underlying all of this, whenever the key amplitude expression that we wrote down is smaller than 0, that corresponds to an index of refraction smaller than 1. So in particular, if the frequency of the light, omega sub L, is bigger than the resonant frequency for our oscillator, you have this effect. For example, when you shine an X-ray through glass, the index of refraction really is smaller than 1. There is no contradiction with causality here, and it's worth taking a moment to reflect on the role played by the speed c in all of this explanation. C is the speed determining how long it takes for an accelerating charge to induce a force on any other charge. Even if there's material in the way, whether that material has an index of refraction bigger than 1 or less than 1, that amount of time that it takes for the influence of one charge to reach another is always the distance between them divided by c. By contrast, the speed that's relevant to an index of refraction is how fast the crest of one of those waves is moving. This is known as the phase velocity. That phase velocity is what determines how much the wave gets scrunched up, which in turn determines how much it refracts or bends, which is part of the reason I think it's very good terminology to call this the index of refraction, rather than, say, the index of slowing. In general, the electric field inside a medium like glass is this incredibly complicated sum of a whole bunch of propagating influences from every one of the wiggling charges in that material, all together with the incoming light wave. But importantly, all of those individual propagations are traveling at c, never slower, never faster. It is miraculous that the way that these combine can be described simply at all, and that it's not some monstrously intractable mess. But we are fortunate, and when you add them all up, the net effect can be described cleanly, and it looks just like a sine wave, one whose phase velocity happens to be different from c. Another thing to keep in mind if it seems very weird for these wave crests to move faster than c is that everything in this explanation depends very heavily on things being in a steady state. That's very different from, say, trying to send information through the medium with a little pulse of light. This is what Mithina explores in her videos on the index of refraction over on Looking Glass Universe, which you should definitely look at. Over there, she talks about how when you express a pulse of light as a sum of many pure sine waves, even if the phase velocities of those constituent components go faster than c, that doesn't necessarily imply that the center of mass of this pulse will itself go faster than c. And in fact, when you simulate the effect of passing through a medium, when the index of refraction is less than 1, what you find is a pulse that goes slower than c, even when the crests within it are going faster. And if that still seems a bit weird, here's an analogy to help see why phase velocity can be way higher than the speed of anything real. Imagine a little machine that has a bunch of rotating arms all extending from a shared shaft. If you view this machine from the side, the tips of all of those arms form what looks like a wave, with crests traveling from right to left. But if I go and reposition the arms to be angled quite close to each other, then you can make it so that the phase velocity of this emergent wave is arbitrarily high, potentially faster than the speed of light or anything else, even when the shaft is rotating at a gentle constant rate, and even when every component of the machine is moving at a reasonably slow pace. Here, it's pretty obvious that such a machine doesn't violate the rules of physics, and that it doesn't let you send messages faster than light. Because the wave crest is not a real object. It's not something that could carry information. It's more of an illusion. The phase velocity in a light wave is similar. Sure, if you shine an X-ray through glass, it is true that the wave crests go faster than the speed of light. But the underlying influences between electric charges that determine the field values in the first place are themselves all bound by the speed c. The most intriguing question of them all, which is how
Yeah. Oh, so now it should work? Yeah. Yeah. Okay. So finish with the physics about it. Do you have, you guys have any question? Was it clear? Yeah. The X-ray. X-ray. The index of, so let me show you that. Yeah. So exactly here, the index of refraction has two parts. It has the refraction part and an imaginary part, which is the absorption. Okay, and the absorption, for those that are doing X-ray imaging, the absorption of beta here is directly linked to the mu. Okay, it's just with wave number and another coefficient, so it's exactly the same units. So you have these two parts, refraction and the absorption, and sinus theta 1 and sinus theta 2. If you have this Snell calculate. See. So what is interesting with X-ray is this part, is the refraction versus the absorption. Okay. If we draw this ratio between the refraction and the absorption for different tissue, might have, for instance, is you see that there is a factor 2000 at some energy, but we are strictly above for the energy that we are using in X-ray radiology, we are above 1000. So in other words, we are deviating light 1000 times more than what we absorb in X-ray. But for the moment, what we measure is what we absorb. Specificity and even with specificity. So this unique property for X-ray is interesting for two main reasons. First, we'll enhance the contrast because we have a factor 1000. So meaning that we are more sensitive. So here is, for instance, rat brain that is imaged at a spatial resolution of something like 6 micron. If we measure only the absorption, this is the contrast that we have, so nothing. Okay. While if we are measuring this index of refraction, we have this very nice image where we can see, for instance, black structures, the beta amyloid plaques here, directly without any contrast agent. Or the other way to use this wave property is to reduce radiation dose. Because we have something that is 1000 times better, we can reduce the radiation, the number of photons that we are using, and still get a good image. So this is a breast, for instance, image at 1/5 of what is normally done in conventional mammography. And this is the contrast that you have with phase, and this is the contrast that you have with that image. Okay. Is there any other question related to this index of refraction? Yep. Absorption, strain. What kind of quantitative information gets from the best contrast? So this index of refraction, so as you can have this Hounsfield units for conventional X-ray CT, you can have a refraction Hounsfield units, like you say, the delta of what, so this is tabulated from, you know what atoms are and so on. So you know, you can do exactly the same stuff, like, so the index of the Hounsfield units is 1000 times the mu of your tissue minus the mu of water divided by the mu of water. And this you can do such a thing with refraction. Okay. What is interesting, I don't have slides to prove that, but what is interesting is that the refraction index varies. So the absorption index varies with the law, which is with the wavelength that is 1 over lambda at the power of 3. while here with the refraction, it's 1 over lambda, which is interesting. We measure this refraction Hounsfield unit, is that it's completely constant with the energy. So if you are able to measure at, let's say, 100 keV, the refraction, your contrast will be the same as at 20 keV, comparing to what you have with the absorption index. See, it's there are many different applications, and we're going to see some of them. We're supposed to make it right. As you like. I don't mind continuing. Now, okay, so as we say, we have this. So how it works with X-ray and how we use these wave properties with X-ray. For the moment, we only talked about the index of refraction, and we'll introduce another index, another type of contrast. So what we are trying to do is to decompose the light matter interaction from this wave perspective. So the first of all, there is, as you said, absorption. Okay, so in terms of wave, what you're going to have is an attenuated profile, and this gives you exactly the X-ray radiography that we always had since then. So by the way, these are images that we obtain at the synchrotron on living animals. So then, now that you are familiar with this concept, we are measuring what we call the refraction and what we call the phase contrast. So what we are measuring here is how the phase has been kicked, okay, as the guy as 3P1 properly introduced. In the real life is the fact that this the straw does not appear straight in the glass of water, and if you are in the water, that's the elements. I mean the objects that you see are bigger than they are. And this gives you another type of contrast, and this is what we call the phase contrast. And this is how the X-ray were refracted in this direction and how they were refracted in those direction. Long story short, if you do this integration, if you do this numerical integration, you have this phase investigation, and you get another type of contrast. Okay. And finally, that I did not introduce yet, is what we call the scattering. Okay? The fact that light in an homogeneous sample the light can be scattered. Okay, and from a wave perspective, what it means that this has been the wave has been spilled. Okay, and in the real life is the fact that in the diffusion and scattering of light in the cloud is different from a scattering in the sky, and the fact that, well, scattering of the cloud here in what, so this is not you see the yellow and the sky is blue. The air is transparent, but the atmosphere is blue, appears blue because it scatters more light, blue light. And what it gives you is this new other type of image, which is the number of structures that are smaller than my pixel that has scattered the light. Here, in the lung, it gives you information, the complete information, and exact quantification of the number of alveoli that my X-ray has crossed. Okay. And this was recently demonstrated in patients by my German friends that made an experiment at the hospital and not at the synchrotron for this chronic obstructive pulmonary disease, which you don't see really well in radiography, okay, with the standard radiography, but with this dark field signal, scattering signal, you see clearly that this signal extinguishes with the severity of the grade of the patient. Why? Because in COPD, what happens is that those alveoli will be filled by water, and then you have less interfaces between air and tissue, And this explains why a healthy lung scatters a lot, while severe COPD scatters less. So the first real application of phase contrast was on mammography because of the promise of going to lower radiation dose. And there was a clinical trial at the Italian synchrotron that showed that phase contrast image, even in radiography, enhance the signal-to-noise ratio, has a better spatial resolution and a higher sensitivity and specificity in general. And this was published in the early 2010. And since then, a lot of studies have shown their interest. We were at the ref the first to show that it was feasible to do phase contrast CT at the same radiation dose that what you do normally radio. Okay. So because we have something that is 1,000 times better, instead of having only two different orientation of the breast, we can reconstruct in 3D this breast. And since this publication in 2012, there were many occasions to show the superiority of phase contrast for mammography. For instance, here is, I don't remember which type of cancer that you see here that you don't see very well in absorption contrast, but in phase contrast, you see really well. Or with this, this comparison in CT on the fresh breast, that you have a better sensitivity, a better delineation, better, let's say, imaging of this structure. And there was supposed to go for 2020 at the Australian synchrotron, a clinical trial for women going to the synchrotron to get their breast imaged. So, just going. But well, in 2020, you know that there was a small thing called COVID, so it was cancelled, and this actually happens nowadays at this, the Australian synchrotron. So some women are being imaged at the European synchrotron to prove that this is useful for imaging, for breast cancer detection, and the fact of this scattering of light was also demonstrated to be interesting for breasts, because in the breast tumors you have a lot of calcifications, and what they could see in this publication, we demonstrate is that they have specificity and sensitivity of 100%, which is questionable. Each time that you have 100%, it's questionable. But they could distinguish the malignant calcification from the benign calcification, thanks to the signature that you have from the absorption that you measure, scattering. So that's, I already talked about it. And what is interesting is that, so this was made in human, but at the synchrotron, it's easy to do such a thing in CT. And these are the results that we get from living rats. So this is the same rats before and after the model. What is interesting is that from the dark field signal, so this scattering signal, you lose a bit the spatial resolution compared to the attenuation. Okay, but what's interesting is that you detect abnormalities that you don't see in the phase contrast, and the absorption would be the same here. So here, for instance, if we look at those two regions, black ones, they have exactly the same value. Okay? While in the dark field method, one is not visible. Why? Because you don't have the enough spatial resolution to see the actual alveolus and how, the state of those alveolus. While the dark field actually gives you a microscopic interpretation of the healthiness, let's say, of those. And what is interesting also with this technique is that due to the fact that we have wavelength that is below the nanometer, we can reach resolution that are not accessible with other, let's say, visible light microscopy. And here are, for instance, images of the lung at 100 nanometers. So here is, for instance, blood vessels, and you see here you see here macrophagus, you see here blood cells. So you can do such a thing for any reason, for any resolution. What we do in my group is mainly work on osteoarthritis, osteoarticular troubles in general, and I will show you some of our results. So what we've done is that we took 3 human hands at the synchrotron, and we imaged them at a radiation dose that is acceptable for the clinics, okay, acceptable for human being. And we compared those images with the conventional CT, with MRI, and also ultrasound, but I will not show you some images of this. What is interesting here, this image, is that you see all the different tissue. You see, well, the bone, okay? You see this trabecular aspect, but also the cartilage, okay? You see the tendons, you see actually the fibers of the tendons. What is interesting also is to see the nerves that are difficult to see here in the carpal canal. And you see some of the microcalcification. We compared that to what was feasible at the image platform, MRI platform. And what is interesting is that none of those sequences is able to depict as well the cartilage. Here, our study was really about the cartilage and how precise we are for the cartilage. And here is this 3D water suppression that is meant for cartilage imaging. What you see here is the comparison is, well, see by eye. Very interesting for phase contrast because you see really well the cartilage, and what is interesting is that you see some calcification and small calcification on the surface of the cartilage, which are not visible at all here in the MRI. And you have a depiction of all the different tissue. If you compare that to conventional CT, well, there is no comparison. The images by themselves. So this was a dual energy CT. So one of the top at the moment. Well, here is a table that summarized the evaluation that we asked to the radiologist and pathologist of Carnegie Hospital. So we asked them to quantify quality of the image for the different structures. Here it was an interesting case because that was for the women had a chondrocalcinosis. So you see really well the calcification. You see some of them in MRI, but only the big ones, as well as in conventional CT. And once again, you see this small calcification on the surface of the cartilage, which is probably an early sign of osteoarthritis. And I like to kid a bit about this fact, because that's, well, with a single modality, gonna roll them all the different images. So here is, for instance, are more or less here. And what we can see is calcification in the anthesis, the height of the largeness of the cartilage, but we see also the median nerve fibers. So you, for instance, for for pathology, for neuroperipheral pathology, we have this. Sorry, I don't know what's going on with this slide. That's and you see some atherosclerosis directly in this artery, which is known to have no atherosclerosis. So it means that probably we were not able yet to see them, not the fact that this artery is not supposed to be. But this property is interesting for many different tissues, and this is an example of what we can get for brain imaging. So in this project, what we've done is to compare. So this is a tumor, brain tumor, and what's to get from this multiparametric MRI that's normal. They do. What is interesting, so as I said, thanks to the fact that X-ray wavelength is really small, is below the nanometers, we can reach very high resolution, and we can perform so what we call now virtual histology, in the sense that, well, we have a CT scan of a small sample, and we can, for instance, see lungs, alveoli, or for instance, eye. So here, these are tomograms, so these are synthesized, but we can perform that. For instance, we have a wall volume. So here is a video of what we can have. For instance, so those are cartilage blobs. So the idea was to see the effects. So we wanted to see in a collaboration that people try to regenerate cartilage. We wanted to see the impact of this growth factor that they have. So these are the images that we have on the left, without and with the growth factor. What is interesting here? So it's a veal cartilage. Okay, it's a veal cartilage. It's a 7 days veal. Okay, so you have all the blood circulation in the cartilage, which in the mature cartilage you don't see. But what is interesting is that you see those black structures. So here, those black structures are actually the chondrocytes. So those are the cells. And these can be done, so as you can see here in 3D, and we can segment all those cells with, for instance, these blood vessels, and study that in 3D, and have not 2D histomorphological parameters, but 3D histomorphological parameters, and to study really the impact of one drug or another on the distribution in 3D of the cells, for instance, or also. And this can be done directly in the joint. So these are images. So this is with a bone window. but you can actually see here the cartilage, the articular cartilage here of the mouse. And you see here the meniscus that are calcified for this mouse. And what we see here in gray is this layer of cartilage that we spoke during the break, and the fact that we see here the convergence. So in this model, we are able to see directly the cells, directly that and the effect of that cells with the drug. Also. And what is interesting is that if you compare to histology, actually, what is interesting is that we see another, see, because when you do histology, so here we are not coming out with histology without decalcification, but here what is normally accepted as the calcified cartilage is this zone, red, which is a bit different from the zone that we see here in 3D. And this is also visible in this image. So we see some cells that are, some structure here. Density is different and gives you another type of information as histology. So that we have to understand it better. And to understand that, we need more and more sample around to see. And what is interesting, and another signal that we not really investigate for this virtual histology is this dark field structure. So this is a standard radiography. No, this is a phase radiography, sorry. What is interesting is that you see the meniscus here, calcified meniscus, but you don't see them really well in dark field. I think that we have here sensitivity to the nanostructure of the calcified structure. Here we see a strong signal in probably due to the hydroxyapatite calcium here that induce a lot of signal dark field scattering, while here the calcified cartilage zone we don't see that signal. That is something that we want to investigate in the future, and that we will do in different models. Another big project, which is really interesting because it's the first time that we can do such a thing, is about the fetal imaging. We are trying to collect all the fetus, the human fetuses and human embryos that we can get from the hospital in Grenoble, because we want to profit of the fact that we have sensitivity to all the different tissue. And this is the result that we get from one human fetus. So here the scale is 1 centimeter solid here and 1 millimeter here. Meaning that we can perform and study for the first time in 3D without degrading the tissue, the anatomy, and the evolution of anatomy for normal case and for pathological case. So the idea is that we're going to have miscarriage, the abortion, and the newborn abortion that are at the Grenoble Hospital. And these are images that we can get. So we wanted to optimize first the protocol for that, and these was done in mice. And here is the resolution that we can image all the human samples. And these are the results that we get from mice. So it's really interesting that you see all the different tissue, all the different tissue with the visibility that you see only with this type of contrast, without any contrast agent, without any marking and on that. Okay, so I think I've made a world tour of what is phase. What are the applications of phase contrast imaging? We are at the beginning of this. We have plenty of application field possible. But well, for the moment, we didn't see it. So we are really limited. And in the next half an hour or till the end of the talk, I will try to explain you how we do it without SLEIGHT, how we obtain those images without SLEIGHT. So to do such a thing, we need to go back to this property. So here, what is important to see. So we are measuring absorption. This is quite easy. This is the number of photons that are crossing, and from a wave perspective, once again, it's smaller amplitude. Okay. And what we are measuring is this phase contrast. Okay, this phase contrast comes from this refraction. But the problem that we have is that with X-ray, frequency of the phase frequency of X-rays is 10 to the 18 Hertz. So possible to detect directly. And to do such a thing, we're going to see how we do it. And for scattering, what is measured is structure that are smaller than the system resolution that we have. And there is this slope that we have for structure, which is a square root of more or less the number of inhomogeneities that we are crossing. That gives you an image, and we will see those images from those sample or those. So first, how do we retrieve the refraction? At the synchrotron, what we do is the same experiments that you are doing on the summer, in the summer, and is using this interference pattern that we see here. What we see here is due to the fact that water is not flat, you see a concentrated beam here and a concentrated beam. In physics worlds, it's interference fringes, but you see constructive fringes and destructive fringes. Okay, what you see here. And the synchrotron, as I said before, the synchrotron is a coherent source, as the sun is a coherent source for us on Earth, because it's big, but we are very, very far away from it. The synchrotron, the source is 60 micron, and we are our detector 1 meters from that. So we can estimate that the light is coming from the same. From that we are facing, try to visible light, is that our refraction is not in the same order. It's microradian compared to radian. So it means that we more or less, the impact point has moved from 1 micron at 1 meter. Okay, so it's very clear. But that's how we obtain those images of the synchrotron, is directly and simply we move the detector away from the sample and collect this image. So this is the signal that we obtain, which is a mix of absorption and these fringes. You see actually here highlighted the contours of the objects in these constructive interferences. And you see here a black structure around that is a destructive fringe. Okay. We can solve an inverse problem knowing the composition of tissue and obtain this image of which is based on the refraction directly and gives you this kind of contrast that we are more familiar with. Synchrotron is cool, but if you look inside what is happening in CT, in normal condition, this is way impossible to image the patients at this speed, and we need really to move from the synchrotron other types of system. So how we do it is by incorporating in X-ray beam some optical elements. I will try to be as fast as possible, but notice they can directly on I'm not clear on that aspect. And our criteria are that we need to have an acceptable dose for patients. We would love to image the patients without dating the patients. And with an excision method that is compatible with the patient. Okay? So for the moment, the first techniques what we can do is work on the source. Okay, work on the X-ray source. So those are the projects. Those are national projects. This one is in France. Famix. They will have the first. They just had the first problems last month. And the idea is to construct a compact synchrotron. Okay, and this has been made in Paris, and this covers only 40 square meters. Okay. And you have the same kind of X-ray source made in Munich that actually funded my postdoc over there, where they have this pocket synchrotron, that's a tabletop synchrotron, to image it. But the problem is that anyway, that the patients, because we will not use another way is interferometry. To do such a thing, they use this grid, okay, like the double Young slit experiment, the famous double Young slit phenomenon. If you place yourself at a certain distance, you measure directly the wave property of your X-ray beam, okay? And you can image directly these phase contrasts in radiography. And so, and interestingly, they just published, in 2022, now 2 years ago, a system that allows you to image a patient within a rotation gap. The moment the acquisition is slow, okay, takes minutes instead of seconds to get the image. But that's very interesting. The problem of this setup is that they need good alignment of those tempers. That's why also it's so slow, because they need to rotate. This has to be aligned at the micron scale, and this at the speed that they need. It's going to be difficult, but still they were able to perform CT scans in 10 minutes, which is more or less the time that we are in BRUN, for instance. And that's the way they did it. And that's the way they did it, radiography, for this clinical trial I was referring to. Another type of setup is this one, is the one that is actually in a clinical trial in London, but not directly on patients, but on surgery specimens. So they are working, for instance, on esophagus cancer. So the idea is that the surgeon extracts, remove some of the esophagus, and then they analyze it directly in the surgery block for the pathologist to see if it was if the security margins were good enough, and in case it's not, the surgeon can modify his surgery. And the idea is rather simple here. The idea is that you have a grid and not use this interferometry pattern. The idea is that they use the simple optical geometry. So you have you have your grid that are aligned perfectly, like that you see all the the first grid generates an array of small. Okay. Then what you have is another grid, okay, just before the detector, and it's aligned. What you see is, and if you desalign the bits, this second grid, what you see is the beams that were detected, that were refracted. And thanks to that, you see instantly the refracted beam. But the thing is that in that case, 50% of the photons, 50% or a portion of the photons that were imaged by the sample are stopped by the grid. It takes those which is the same here. Actually, only 25% of the photons that were used to image the patient are actually collected. Okay. And us, that our methodology is, well, okay. This is a very difficult optical problem. Let's do this problem numerically. So the idea, our idea is optimal in the sense that there is nothing between the sample and the detector. So every photons that are crossing the sample are collected, therefore fast, and 3D is performed easily. So the idea is this one. We take a matrix, a membrane that creates a pattern. Okay? This pattern, and then we put the sample without moving the rand, without moving the mask. We put the sample in the beam. Okay? And then we collect an image. And this procedure can be doubled, or we can have that at multiple different image acquisition. And how it works is this way. So here what you're gonna see is image with and without the sample. If you have an absorbed beam, what you're gonna have is loss of intensity. Okay? If I zoom in the membrane, I get this. If I have refraction, what I have is what is local displacement of my population factor. And if I have scattering, what I'm going to have is this blurring of this scattering, of this membrane. So in a way, we have all the information. If another way to look at it is that we take an image reference, okay, take a profile of it, we have this profile. Okay. If we do the same for the sample image, we get another profile. If it was refracted, sorry, if it was absorbed, you see a loss. If you have refraction, then the peaks are not at the same. And if it's scattered, then you have a blurred structure, and the contrast between is small. So we have a simple experimental way to do this phase contrast without fancy optics. And we solved, and we translated this very complicated physics problem into a numerical problem. And these are, for instance, so we collect couple, or you're gonna see that at the end now are not only a couple of images is needed, and how we solve those images. So the first methods that we were using is this are those ones. Those familiar with particle image volume. Is the same. So what we do is that we take a subset of the image all segments in this image. And then what we do is a cross correlation. Okay? Like that, in the cross correlation, we have then how the beam was shifted from by the sound. And if we use such a beam, then we have everything. Then we can measure the refraction is directly this vector. Intensity is the difference of the beam that we have here. And the scattering is the standard deviation that we measure here in the subset, and the standard deviation measured in the outer subset. As it was at the time, 2015, 2017, it was very difficult. I mean, it was computationally extensive. We tried to model that with implicit methods. So instead of having these explicit methods, trying to solve for each voxel, this cross correlation and so on, we try to model this. This is how normally, so this is, by the way, how it evolves with the propagation. If you have here a wavefront, you have the objects directly after the beam, you have this, and then you start to have this interference index. Okay? In equations is this one. Okay, this is called the transport of intensity equation. Was mainly used since it is mainly used since the 1980s, and here for X-ray, in our case, it was translated with the difference between the image reference and so this is sorry. So I'm too fast. This is the propagation-based imaging. So this is just by moving the paper away. This is the how it evolves with Z, the propagation distance. Okay? A simple way to measure that is to go back to these phase maps, is to solve this kind of equation where you only do this is a Fourier map, this is a Fourier transform, and this is the paper that founded a seminal paper in 2002 by David Leganin. That's all the synchrotrons in the world are using. Okay, and this is just with a single paper. We worked with David on the formulation and how to adapt this method while we don't exploit the Z, but we measure the difference between the reference and the sample image. And this goes with this equation. And the idea is that what hypothesis is here is the difference between the reference image and the sample image. It's just the gradient of the reference image times the refraction caused by the sampling. And this is our kind of long story short, we can do different approximation to solve this PDE, and we have this fantastic image of the ball or radial graph of the ball, and then we can experiment. But this was just for the phase. Then we can incorporate in the model another term, a diffusion term, scattering term, that express how this dark field signal will appears in the equations. And what we have here is this. So we had an extra term, this one, which is the negation of the dark field of the sample. This is the MO, and the reference image. Okay. What we have here is this one, and the result that we have is those ones. So, for instance, this is interesting. This is an interesting experiment. We had this bulbs, this and what was interesting is that we thought that this will create some signal, but at the resolution that we were, actually it was not, because we were resolved enough to see the velocity here. But we were not able to see the micro porosity that you have in the middle parts. Not the pores, the pores that you have, but the very tiny pores that you have in the wall. Here, I don't know if it's very visible, but these are results of so bizarre Nespresso capsules. Obviously, we do not have the resolution enough to see the grains, the coffee grains. Okay. What is interesting is that with this term, this dark term, what we see is a loss of the speed. Okay. Here, the dark field signal is not the same here than here. Why? Because the grains here are smaller than this one. Okay. Because if you remember, the equation, the model was that it was the square root of the number of porosity that we have. Here is that means that less here we have less pores, so here we have smaller. And these are the results in vivo of mice. It's not the mice, it's blood. Plus, what we see here, this experiment, what is interesting is also this box hairs. Mouse, you can see well, they don't have been made, but they create large scattering of the easel. So we have to shave the rats. Then we can either complicate this term and use it as a tensor and look at the orientation. And these are the results that we have. So here, let's concentrate for a moment on the left part. So this is a Haribo crocodile candy that everyone has. Yes. Interestingly, what you have, the white part and the blue part here is exactly the same matter. The only difference is the porosity. Okay. And as we are cannibals, we put a toothpick in the head of the okay. What is interesting is that if we solve this ugly, nasty equation, what we see is that we can measure how the orientation of the scattering angle. Okay? And what is interesting is that the porosity of the white matter is same in X and Y direction. While if you look at it, you have for toothpick only one main direction. Here in this color map, you see only green. Why? Because the wood only scatters in one direction, which is orthogonal to the fibers of the wood. Okay? And we obtain the same results on tooth. Tooth are organized material. Is in the dentine part, you have canals that are 2 to 5 micron. And here I have a pixel of 75 micron. So I'm not able to see. I'm not able to see directly the canals, but I can here see their orientation. And I can see how many there are. Okay. And this is also interesting for bone. This aspect. And then, so for the moment, I showed you only images of 2D, but these are visible in 3D, and these are the results that I've shown you on the setup by the Germans. It's visible in as well, and it's interesting in 3D because also we can probably this orientation stuff see some material or the scattering properties different methods. So this is really the future of what we are doing. Phase is interesting. First, the dark field is really new. We are just at the beginning of the story. So to go outside of the cyclotron, we recently had a collaboration with a company named Xenox. They are from Canada, and what they do is devices for X-ray small angle scattering. small angular pixel scattering is useful to study the size of the nanoparticles, for instance, to study the nanostructure. What we have done is to adapt our methodology from the synchrotron to the device. And what we used is this new type of this new source, which is more or less a standard trace source with an energy which is smaller than what we are usually dealing with geology, but good enough, let's say, to do virtual storage. And so the idea is that we obtain on this image and we incorporate this membrane, their setup, and analyze the pipe and did the analysis pipeline for automatically numerical pipeline, perform phase contrasts and dark field CT out of the synchrotron. And here are, for instance, the results. These are results on, so they are not interested in biological applications, but these are some results. So this is the cheese ball from this aperitif. And this is the image that you get from attenuation. Okay, this is the image that you get from the refraction. What is interesting, for instance, here is the dark field. Here, what you see is salt grain. Okay? And it's typical, you see that it's visible mainly in the dark field method, because otherwise you would not see that information. And ACL is very, very low in terms of number, but you see that as a crystal dark field method. And the company is also American. And this is what you get from, so these are impacts of bullet impact from a gun on plastic, and what you see here is the orientation of nice orientation of how the fibers are started by bullet impact. Then if you want to have a special resolution within Optus. And now we have this very nice project financed by the Renewable Algae Index. And the idea is to build out of the synchrotron on the campus at Université Grenoble to develop a new system where we're going to have all the tools to perform phase contrast imaging at the energy that is useful for human imaging in H. And like that, we're going to have resolution of 1 micron, 100 micron, with a versatile system, and actually we'll have experience also part of the foundation because we have vectors. And the main application for the moment that we are that we will deal with is this dental imaging project. So we had this idea funded this year that will fund the PhD of team to obtain those kind of images outside of the synchrotron and to build a real clinical prototype of phase contrast imaging outside of the synchrotron. Why we are dealing with this parodontitis? Because it's as osteoarthritis, a chronic inflammatory disease that affects all the different tissue, mouth, bone, teeth, and also dental. And it's going to be a perfect demonstration that we are able to see all the different tissue at the clinical levels with a clinical prototype outside of this. Okay, I'm going to use the last 10 minutes to see. I showed you so far two different approaches. One is based on the particle aspect of light, this photoelectric effect. The other was using wave properties with the phase contrast. And actually, in the future, the near future, we're going to use actually all those approaches to have better images. And this is, for instance, an example of what is visible. Here is an image of gold gold, liquid, and plastics. Okay. And what they do with only one reference is to separate gold, have a gold image and a plastic image. Okay. Have a concentration directly with only one image. Okay. Contrary to what we were able with spectral CT, they were able to do it at only one purpose. So the idea is to look how they do it is to combine this phase contrasts, its refractive X-ray and this vision computer. How they do it is this idea. Here is the value of above the delta and the beta bar from the index of refraction. What is interesting is that if you have one energy, these are the values that you have for the refraction and the absorption for one material. If you have in a box of certain concentration of aluminium or bone, it will follow this line. Okay? Meaning that if you are able to measure how the image is refracted, one image, if you are able to decompose how it's refracted and how it is absorbed, we have two kind of equation. You have an equation for sum of the refraction and for the sum of attenuation. Thanks to that, you are able then to do and have this direct conversion. If you have only one image, you can it goes into so it means that you can in the future use more contrast agents than the number of bits that we have in our spectrum detector. Meaning that we can exploit that to have a large amount of contrast agent that will be targeted to some, for instance, some functions. Time for questions. Well, we have seen that wave X-ray imaging is a formidable tool for exploring biological tissue from medium to high resolution without any problem. The thing is that we are dealing with very new signals and to define semiology, what is typical from contrast that we have. Seen that the transfer of these synchrotron technologies to conventional systems are really in the process, are currently happening. And well, if you guys are interested in new case where X-ray imaging can be addressed, would like first to finish by thanking all the young people that have been to supervise and all the people that I'm working with. That's first all those images. Thanks for
Thank you very much. Thank you very much. It's impressive. Do you have questions? Yes. Donat.
Thanks a lot for this very interesting presentation. I had a question on where you were showing, for example, the chondrocyte. I don't remember the number of the slide, right? But where you were showing the chondrocyte, that could you? I know that. We know that there should have been chondrocytes, but can we say that, for example, we could use the phase to discriminate different cell types? So can we get an information from the from let's say the phase, I call it phase, maybe I'm mistaken, but on the composition, for example, of different cell types to inform the attribution of the different cell types.
So if you, for the moment, We have only access to the morphology. So depending on the resolution, introduce some images, for instance, a scheme where it was resting for in the based on the morphology, the pathologist at a certain resolution can distinguish. Otherwise, what we are trying to do now is to use nanoparticles with antibodies, as you can and use this as a marker, and that's so far what we could see, and for the moment it's not published. We used a brain model for creating inflammation, and we used antibodies with nanoparticles embedded. And what was interesting is that we could see that goes only in the group. That's just the beginning of the start, and for sure it is interesting, but we need to invest a lot to get to this. I just wanted space. Because we were able to see the macrophages, instance directly. We need to go back to this this case of this chondrocytes. We want that types of cells we need to build at higher resolution, which is not impossible. Here, what was interesting is that this resolution is flexible. If we want really to go higher and see different types of cells, resolution that's needs. It's very balanced resolution. So this is
Yeah, thank you. It was very nice. So in the picture where you showed this hand with hard and soft tissue, maybe I didn't see that really, but it seems that the bone marrow was black. Can you see, for instance, where the bone marrow is hematopoietic or where it is fat marrow? Can you distinguish between both? Also in the hand, maybe there are not these two types of bone marrow, but would it be possible?
well, so to answer your question honestly, I don't know if it's possible. For sure, I mean, all the images that I've shown you were so done post-mortem, so probably also affects the position also of the bone. So that's, I mean, honestly, I cannot answer yes. Well, if you want, we can test. I don't see any obstacle. Not to see it.
So I've got a question about the method you use with constics behind the analyzing the constics using the index of function. Does it have trouble when there are discontinuities in the index? So I don't need to have a step of the deviation of the direction of the light rays.
With X-ray, the angle is so small that we see those discontinuities really affecting our images that we are human preservatives. So for the moment, we never had some problems. The problem that we have is phase contrast is sometimes that we have phase blocking. So phase shift that are more than 5, but this can be done. So,
Well, thank you, Emmanuel.